Hello everyone, today we're going to be learning about Legendre's formula. So let's start with our problem. Find the number of zeros at the end of this factorial operation, which is a 1000 factorial. So if we can recall, a factorial operation is where we take a positive integer and multiply it with every positive integer less than it. So given that, 1000 factorial seems like an insanely large number. In the previous lesson, which watch that if you haven't already, we talked about trailing zeros and how they can be found through the prime factorization of 10, which is 2 times 5. And we determined that the number of factors of 5 corresponds to the number of trailing zeros. So although this logic still applies, manually finding multiples of 5 and factoring them would take a lot of time, especially with such a large factorial number. So how can we solve this more efficiently? Well, before we get into that, we need to take a look at the floor function. The floor function takes a real number and maps it to the greatest integer less than or equal to it. So it's essentially the process of rounding down to the nearest integer. So here is kind of the core definition of a floor function in the form of an inequality. That states the floor function of x is less than or equal to x, which is less than the floor function of x plus 1. So let's see how this would apply to a number, say x is equal to 2.4. So first, let's find the floor function of 2.4. The floor function of 2.4 would be 2 because we're rounding down to the nearest integer. Now if we put this in the inequality, we'd get 2 is less than 2.4, which is less than 2 plus 1, which is 3. This also works for x is equal to 2.9 with the floor function of 2.9, or let's make it 2.99. The floor function of 2.99 is still 2 because we are rounding down to the nearest integer. So this would get us, with the inequality, 2 is less than 2.999, which is less than 2 plus 1, which is 3. So this was a brief demonstration on how the floor function works. Now, here is where we have to be careful. Before getting into what's written over here, let's just take the prime factorization of some multiples of 5. So for 5, we have 1 times 5, and that gets us to 1 factor of 5. 10, that gets us to 2 times 5, that gets us to a factor of 5. With 15, we get a factor of 5. With 20, we get a factor of 5. But wait a second, with 25, we get 2 factors of 5. And this additional factor of 5 is counted in when we're finding our number of trailing zeros. So now what we need to find is every number between 1 and 1000 that holds at least 2 factors of 5. Now how can we do that? By taking the floor function of 1000 divided by 25, because we can realize that every 25 numbers we get an additional factor of 5. So this will get us to 40. Now we can continue this applying the same logic where we see that 125 has 3 factors of 5, so an additional factor. So to find every number between 1 and 1000 that holds at least 3 factors of 5, we can take the floor function of 1000 divided by 125, which gets us to 8. Now we continue this with the floor function of 1000 divided by 625, because 625 has 4 factors of 5 in its prime factorization. So by now, a sort of a pattern should be evident to you. We're always dividing by the next power of 5. First, we divided by 5, which is 5 to the first power, then by 25, which is 5 to the second power, then by 125, which is 5 to the third power, and now by 625, which is 5 to the 4th power. And that's because with each increasing power, we see an additional factor of 5 being added. So again, we have the floor function of 1000 divided by 625. That gets us to 1. Now, how do we know when we're done with this process? How do we know when we've found every factor of 5? Well, for now, let's just continue finding 5 to the 5th power, which is 3,125. So every number between 1 and 1,000, that holds at least 5 factors of 5. So right off the bat, we realize that 3,125 is greater than 1,000. So dividing this would result in a fraction. So fractions are less than 1. So that means when we are rounding down with our floor function, that would just get us to 0. Now, we could continue doing this again and again, but we're really just going to keep getting 0. So that means that we found all the multiples of 5 that have up to 1 to 4 factors of 5. Now we need to calculate the total number of factors of 5 by adding all of the results of the floor functions together. And this is because the floor functions found how many multiples there were with factors of 5 and extra factors too. So let's start adding that. 200 is where we had the multiples with 1 factor of 5, plus 40, which were multiples with 2 factors of 5, plus 8, multiples with 3 factors of 5, and 1, multiples with 4 factors of 5. And that gets us to a total of 249. So this gives us the total number of 5s that come with the factorization of 1000 factorial. So we can determine that 1000 factorial has 249 trailing zeros. Trailing zeros. But here we didn't just find the trailing zeros, we also used what is known as Legendre's formula. So let's take a look at it. Okay, so here is the formula. And although the notation looks intimidating, the process is the exact same as the steps that were shown earlier. With this, you can also solve problems beyond just trailing zeros. So let's just kind of look at really what the parts of this formula represent. So this part, with v meaning valuation, represents the highest exponent of the prime number p that divides into n factorial. Then with the floor function of x, that's really just a representing of the floor function over here. Then p to the I power is increasing powers of the prime number. So again, p is our prime number and I is our increasing powers, like we showed earlier with the powers of 5 increasing. Now, this part of the formula, don't worry about it too much, but it really just means to repeatedly add the results of the floor function with the power I increasing by 1 each time. Okay, now let's try this practice problem for fun. Find the largest integer for k, which 2 to the power k divides into 27 factorial. So we can use Legendre's formula for this. And why? Well, because 2 is a prime factor, and we need to find how many times it appears in the factorial. So let's kind of write it in the form of the equation, or formula. So we have our valuation, we have our prime factor 2 and factorial 27, or 27 factorial, and we're just going to write our floor functions like we did in our steps. 2 to the first power plus the floor function of 27 divided by 2 to the second power plus 27 divided by 2 to the third power plus 27 divided by 2 to the fourth power. And we could also write 2 to the fifth power, but 2 to the fifth power is 32, and oh, got cut off, is 32. And we already know that 32 is greater than 27, so the floor function would just result in 0. So now let's write this out. Write out our total number of factors of 2. And that gets us to 23. So the largest integer for k, which 2 to the power k divides into 27 factorial, is 23. Now feel free to try this practice question in the quiz feature on YouTube. Find the largest integer k for which 3 to the power k divides into 120 factorial. And I'd like to encourage you to use Legendre's formula for this one. That's all from my side. Bye!